Okay, so today we'll have announcements and then just a tiny bit of chapter 6 and then chapter 7. All right, so the SN2 reaction can't happen with the tertiary electrophile. That's what I've been saying, right? The tertiary electrophiles just have too much steric hindrance. The nucleophile can't get back in there. So like, for example, this one, I got a good leaving group of bromide. When it comes off, it's a very weak base. But because it's tertiary, even a really strong nucleophile, which has a negative charge, carbon's polarizable, not too electronegative, it can reach its electrons out. Even with such a great nucleophile, this tertiary electrophile is just too crowded. The cone of reactivity is too small, so it just keeps bouncing off these methyls. So we say, and pretty much every textbook and every professor always says, no, there can't be any SN2 reactions on a tertiary electrophile. It's just the hard, fast rule. It can't happen, right? But wait a minute. People said the world was flat too. And then they proved it wasn't. But now they might say it's flat again. Who knows, right? I think I do. I think I see the curvature. Maybe I'm imagining it. But when you're at the ocean, sometimes it looks like it curves. Or is it? Or is it? And can you do an SN2 reaction on a tertiary electrophile? So since chemists find out something like a stone, like a brick wall, oh, we can't do SN2 on a tertiary electrophile, then they go out and hunt for the exception, right? They're like, oh, or if they stumble, usually you stumble across them. You're like, wait a minute, was that an SN2 on a tertiary? So there was this publication I saw. This was cool. I just came across it, and it's by Michael D. Toney, who's a organic chemist at UC Davis, where I was at grad school, and I actually TA'd for one of his classes. He was a cool dude. We would grade the exams together in his office, and he'd have his dog come in like at night. He'd have his dog with him down the hallway into his office. But Dr. Toney and his group, they came across an SN2 reaction on a tertiary carbon. So you can see this is a pretty crazy looking electrophile, huh? And that oxygen has a plus charge, so it wants to get rid of that plus charge. It's really pulling those electrons. And he's got a really good nucleophile, azide. But let's look at it a little more deeply. Yeah, and he published this in Journal American Chemical Society. That's a big journal for chemists. If you get into that, that's a good one to get into. Back in 2010. And so a little more detail. Where's the lone pairs? Dr. Toney. It's okay. He's just he's found the reaction. So we got a lone pair on that oxygen, right? At the plus charge. And then I'm going to show it on the azide too. And here we'll get 2 lone pairs. So how do we know this is? Well, here, let me show you azide first. So that's azide. We've seen that before. Very strong nucleophile. Either end can react in the nitrogens. And but how do we know it's SN2? Well, it doesn't look completely like it is, but this bond right here, it's wedged to the oxygen. The oxygen's coming out at us. And so this nucleophile, when it adds, it winds up dashed. And that suggests SN2, because if it was not SN2, if it was another reaction, like we're going to learn about SN1 today, then you wouldn't just get the dashed azide. You get dashed azide and wedged azide. So when you just see only the dashed, like inverted like SN2, then you're like, oh, wow, we got an SN2 on a tertiary. So kind of interesting, right? Okay, so I said a lot of this before, so I'll go quickly through this beginning stuff. And I haven't gotten anything on the chat. Is everyone hearing me? Those of you here? Is everything going good? Thank you. Okay, good. All right, so don't skip lab questions. I said that before. It's like going to the movies with your eyes closed. So tablet users, try to use different colors when you answer stuff and see if you can make smaller files, or just type up your answers separate from my big file. And it's best to watch lectures before lab. I even send out an announcement like that before lab if you can, but if not, at least go through the lecture outline like I'm doing now. You'll see it's going to be worth it. So homework E chapter 6, let's do this Wednesday, Thursday. You definitely want to turn it or work through all those problems before then, because that's going to get you ready for exam 3. It's crazy when people turn in like home. They say, oh, I haven't quite finished the homework to me after the exam. I'm like, oh yeah, you should be doing that before the exam. And you can come do lab work as always early. We got the mechanism quiz today, SN2 reaction. So remember that this is the animation, and it has the quiz at the end, and then so you know exactly what you got. I got it all printed up right here. So no secrets here. You know exactly what you're getting. You come in ready to do well on that. That'll really help you get ready for the exam too. And Annalise, you're asking about homework E due this week. Yes. So you want to definitely do homework E this week, Annalise, because that's over chapter 6, which exam 3 this week is over chapter 6. So you want to do that. And then exam 3 details. I gave a lot of these before. Come early if you want. And also this exam, it's maybe a little bit longer than the first 2. So if you felt like you were using up a lot of the lab time last time on the other exams, maybe if you can, come early to these ones. Place your cell phone at the front again, come in quietly. It's going to be cumulative, but focus on the most recent chapters as always. And I gave this out before. I like this kind of question. Zigzag to Fischer or back. Radical halogenation. This is going to be a big one. The radical halogenation of alkanes with StereoChem. So practice those. I got a bunch of examples for you. It's actually, I gave you so many examples of this reaction, it's hard to come up with a new one for the exam. But I did. All right. And then I like these StereoChem questions too, right? As I was going through grading the homework, it seemed like those who turned it in later were doing better. Those who turned it in early were struggling a little bit with that. I've talked about it since then. And then I really like these questions. This was the question that kind of got my job here. And SN2, be able to rank all that stuff. We already talked about this last time, but I did add a little bit more to this. So, oh yeah, I said last week that I'd do some SN1, E1, and E2, and I do want to do that. And I try not to have too much material. The lecture the week of the exam, like today's Monday, and now you're going to take the exam Wednesday, Thursday. I try not to add too much from that lecture because I want you to have time to digest it. But with this one, I really want you to know these mechanisms, and it's just a matter of practice. So this is it's going to be, you know, it's more for you to get to do on the exam, but it should be easy points because I'm telling you the exact questions I'm putting on the exam. This is like WikiLeaks. This is like it's like Chegg right here. You got the Chegg answers right here. So if you look, number 9 on your exam on Wednesday and Thursday will be this exact question, the E1 mechanism. And I even tell you what reaction it is. Okay. And I'll be going over these mechanisms today. So you'll want to practice this. So you know this question's on the exam, just like our quiz today, you know exactly what it is. So you just practice it. And when you get to the exam, it shouldn't be something where you have to like figure out. It should be just like, okay, here we go. Let's do it. Like when you're playing an instrument, if you have to think about where each finger goes to play the C key, you're not going to be able to play the piano right. You know, you got to practice till you get to that. All right, so O-Chem leaks continued. We got the E2 reaction I'm gonna go over today and the SN1 reaction here. I made these really simple molecules too without a lot of products, so it should be pretty easy. And then I'll probably throw on a reaction coordinate diagram, energy versus reaction coordinate diagram, where you got to like, where there's charge involved. So you're like, oh, is that guy gonna be plus a quarter, minus a quarter? Oh, I wonder why that one didn't get smaller. Yeah, whatever. And a little bit longer. So yeah, as I said, practice. So you come in ready to go. The basic ones, like those 3 I just gave you, those shouldn't take you long. Those should be like, it's just as quick as you can write them, you know? And yeah, it's all about practice. So know the curved arrow mechanisms to the point where you don't have to write them out. You can just see the entire process in your head. It's like an SN2 reaction. It's just one step. I'm hoping you can already see the nucleophile hitting the electrophile backside, leaving group leaving. It inverts, inversion of configuration. And now the SN1 and the SN1 and the E1, they're a little bit longer mechanisms, just a couple steps though. Nothing like halogenations. But the SN1 and the E1, they're a little bit longer, so you got to practice them. And then the E2 is a one-stepper again. But if you don't practice, you're not going to do well. Bring colored pencils if you got them, because I'm asking you to use color like you saw in the questions. But if you don't have one, for whatever reason, I'll loan you one. All right, and then I really want you to do well on this exam. We're at that point of the semester where it's do or die, and I want you to do. Let's do this week. So I'm I'm gonna have some extra office hours to help you out. So I'll have an office hour tonight. Basically, when my lab ends at 5:05, I'll just hang out a little longer. So if you want to jump on Zoom, you can. I put the office hours in Zoom or in Confer Zoom. Or if you're on campus or around, you could just come over here too. And I'm going to be doing that tonight and tomorrow night. So, yep. And I'll have my normal office hour tomorrow morning. So come and practice the Confer Zoom. So we got extra office hour tonight, office hour tomorrow morning, extra office hour tomorrow night. And then we still have the lecture Wednesday, but the exam will be in lab afterwards. I won't put anything from this lecture on exam 3, but it'll be, if you go to that lecture, you're going to still be learning. It's still prepared, it'll still be helpful for the exam. All right, so, I got an E1 reaction mechanism and the energy versus reaction coordinate diagram from a student of ours. Wait a minute, I'm going to do it differently. Skip that, yeah. So if we go to, I'll back it up. If I go to our organic chemistry step-by-step, and I go to animations, we're going to get more of these animations and things, helpful things on here as we go, because we're getting later into chapters. So if I go to sheet 2, see I'm on sheet 1 here, head over to sheet 2, and chapter 6 has got a lot of stuff here, right? From fall 2020 and fall 21. We got James's SN2 there. And then in chapter 7, I got a lot of nice stuff. And look at that. Oh, wait. Why did I put James there twice? Yeah, that goes in chapter 6. Delete. All right. So, but I got Inslee's. So I showed you James's last week. Let's check out Inslee's real quick. And other honor students, get me those honors projects. It's going to help you for the exam. All right, so here we go. E1 reaction by Inslee Jang, fall 2021. Here's the overall reaction. Again, it's a substitution, and we'll talk more about why heat is important. And you wind up, it's not a substitution, I'm sorry. I said substitution, not a substitution, it's elimination. So you're gonna eliminate a hydrogen and a leaving group, or the proton of a hydrogen. And so check it out. How many hydrogens are on this methyl up top here on the reactant side? How many hydrogens are there? We have 3 hydrogens right there, right? Now how many hydrogens on the product? So that was a methyl before. How many hydrogens does it have now? 2 hydrogens, huh? So it's got 2, it had 3, and now it has 2. And then the water had 2 hydrogens. How many does it have on the product side? 3, yeah. So do you see the water is going to be taking a hydrogen from that carbon? And then the leaving group left. So here's the mechanism. So the first step of the mechanism is the leaving group just leaving all on its own. And this happens to be the rate determining step. Seems like it would be, right? Because it's, it's kind of crazy just popping a leaving group off like that. And that's how it works. That's a unimolecular rate determining step. There's only one reactant. That's where the 1 comes from, E1. And so if we color code this bond green, we add these lone pair red. This is what happens. Add a hinge in there. And we're going to deprotonate this hydrogen because we have 3 currently. We're going to only have 2. And then that pi bond, this sigma bond is going to swing down and become a pi bond to the carbocation. So you're breaking the carbon hydrogen bond, but making an OH bond. And think of the sigma bond as having a hinge there. There we go. We got our alkene and our leaving group. Oh, wait. Oh, no, that's it. No, that was it. Yeah, a double bond formed. So we wind up losing a proton. And in the first step, you lose a leaving group. So you're eliminating parts of the molecule. Here's the energy versus reaction coordinate diagram. So the very first step, let me go back. Is this first step exothermic or endothermic? This rate determining step here, what do you think? So we're breaking a bond. Does it take energy to break bonds, or is energy released when you break bonds? Yeah, energy, you need to input energy to break a bond. So this is definitely going to be an endothermic step. That first step's endo. So all we're doing is breaking bonds. And the last step, it's hard to tell because you're breaking a CH, but making an OH. So it depends on the bond energies, and it winds up it's exo. So here's our initial tertiary electrophile, and then our carbocation and the iodide leaving group, and then the water is going to be used for the next step. And so here's our curve. And now a lot of people make a mistake with this. Where should I start my activation energy? Should I start here? Arrow, when I'm talking about going in the forward direction, it should start with the reactants, right? So that's the correct activation energy to that first transition state. And now this second one, this is where people mess it up a lot. A lot of times they start with the activation energy down here or here. That doesn't make sense, right? What we're talking about now is water and the carbocation reacting and gaining enough energy to overcome the activation energy. So activation energy starts here. Oh, that's the EA of the rate thermostat. And there we go. And then that's it. And then the transition states, the first one looks more like what? Reactants or products? Looks more like products, right? So it's going to look more like a carbocation and an iodide minus. So it's going to look, going to have that bond's going to almost fully be broken. And my charge on the iodide, I don't know which one comes up first. Let me see if I can do it. Oh, you didn't see it, did you? So what's the carbon charge? Is it like plus 3/4 or plus 1/4? Yeah, plus 3/4. And the iodide, is it going to be minus 1/4 or plus or minus 3/4? Yeah, minus 3/4. It's going to be closer to -1 because it's looking like the product. And you know what? I'm going to be anal about this. I like red for some reason for negative and blue for positive. I don't know why. Let's go positive. Oh, come on. Yeah, good job, Ensley. But did you get the memo about the TPS cover sheets and the charges here? Just kidding. All right, so here we go. So for this one, it's going to be more reactant-like. If you remember that next step is exothermic. So the water is going to be deprotonating. And so it's going to be, this hydrogen is going to be closer to the carbon it came from. And you have to show the bond between the hydrogen and the carbon breaking, the bond between the hydrogen and the oxygen breaking or making, and the pi bond making the pi bond here. This is one that people get tripped up on a lot, but got to show all bonds breaking and making and making. So it's closer to reactants, which was +1 for the carbocation. So it's going to be plus 3/4. And then the other thing that changes charge is the oxygen of the water. That's going to be +1/4 because it's only just starting to make its bond. It's only just starting to get positive. So good job, Ensley. That was good work. All right, you got a little preview already for the E1 there. And okay, any questions about that intro? All right, let's get going. So I'll get to my Jamboard. Would you like me to give you an answer key to the questions on the exam? Does that sound good? OChem leaks week. Yeah, let's do it. Okay, so the first one. Which one's that one? E1? Yeah, I might as well do that one first. I'm going to go over these now because this is going to get you ready for this exam coming up. And then I'm going to back up. After I do this just basic mechanism, then I'm going to back up and go slower through them and talk about the details of it. But the key is just, the thing I really want is just to make sure you start off with a real good, solid understanding of the mechanism. And then once you have that, the details will make more sense. All right, so for this one, we just went over Ensley's excellent Google slide animation, so you might be able to do this one as is, huh? Let me turn on my iPad. I went and saw my mom this weekend down south in Phelan. I don't know if you've ever heard of Phelan, California, out in the middle of the high desert, where the Mojave Desert meets the mountains. That's what they say at the grocery store on the big wall sign. But now I'm back. Just flew in, so I'm tired today. So I might be off. We'll see. Okay, here we go. So I'm going to number these carbons because it's so easy to leave off a carbon or add a carbon. But if I number it, it's going to be much better. And what's going to happen here is I'm going to lose, of these 3 methyls here, I'm going to lose one of their hydrogens. And actually, I'll just do the mechanism first. I think that's better. I'll lose one of those hydrogens off the methyls. All 3 methyls are equivalent. I tried to make this one really simple like that. And I'm going to color code that as blue. And the first step of the reaction is a unimolecular step. It's the rate determining step. And what happens? What do I draw? What's my curved arrow here? Chlorine just leaves on its own. There we go. And so we wind up with what's called a carbocation, and then the chloride leaving group. So this chloride, do you know of it as a strong base or a weak base? Oh, no, not a strong base at all. Very weak base. Its conjugate acid is hydrochloric acid. Remember, that's one of our strongest acids. So if you're a very weak base, then you're a good leaving group. Remember, that's how we figure out leaving groups, take them off and check them out in terms of their base strength. HCl, remember, HCl has a pKa of about -7, we memorized. Very strong acid, so very weak base. And also, if it was a strong base, then our salt on our fries would like saponify our tongue. Everything we ate salty would be turning our fats into soaps. Everything would taste like soap. All right, here we go. Now the next step, water comes along and it's going to deprotonate 1 carbon away from where the leaving group was. So the leaving group was right in that middle, right? This is a tertiary electrophile. Tertiary electrophile, right? The leaving group is left, and now 1 carbon away you can deprotonate. So I can deprotonate here, here, or here. Sometimes students get confused and they try to deprotonate where the leaving group was, or 2 carbons away, but it's got to be 1 carbon away. So you don't get mixed up on that. So here we go. I'm going to draw out a hydrogen 1 carbon away. I'm going to add on a hinge too, so hopefully it'll make a lot of sense. And this is how it goes. The water molecule deprotonates this hydrogen. This hydrogen now, it's relatively acidic because of the carbocation of its neighboring carbon there. This carbocation is like an electron vacuum. It's sucking electron density to it, weakening the CH bond. And then this green pair of electrons is going to swing down and make a pi bond. And there you have it. So I want you all to write exactly this mechanism on the exam, Wednesday or Thursday. And you don't have to write all this details, I'm not asking for this stuff, but just, right here, this should be like, oh, it's coming. I know it's coming. I'm going to nail it. Okay, so yeah. And then once I've done the mechanism, then I can come up here and draw in my products. Oh, you know what I'm going to do? Sorry, I forgot one other thing. I'm going to number all my carbons. Let's go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, that looks good. And then if I come up here, I can draw my products again to the overall reaction. I know it's repetitive, but this is how I want you to do it. that's everything. Oh, I was gonna number these two. 1, 1, 2, 3, 4. All right, there we go. Done. 10 out of 10. Easy money. Okay, that's the E1 reaction. I'll come back to the E1 and tell you a little more about it. But for now, that's for this exam coming up. You don't need to tell me about the details of it. You just need this mechanism. Now let's go to the next one. This one, before I do E2, I'll do E2. Yeah, that's a good transition. Oh, shoot. Decided to throw my Apple Pencil at the floor. Hopefully it works still. How many are going to be coming tonight or tomorrow to extra office hours? Nice. Okay, I'll see you there. I'll see you there. Okay, 1, 2, 3, 4. It's the same electrophile basically as before here. It's just I added an iodide leaving group just to give it some flavor. Okay, and now this is an E2 reaction. It's elimination again, but this time it's going to be what we call a bimolecular rate determining step. So I'll show you what that means. Draw this up the way I want. I want to go. Yeah, I'll do that. So it's still an elimination. I'm still going to make an alkene. I'm going to make the exact same product as before. And but it's bimolecular, so 2 molecules are reacting at the same time. So what's going to happen now is the hydrogen, that's 1 carbon away. Here's the carbon with a leaving group, 1 carbon away. That's going to be deprotonated at the same time as the leaving group leaves. It's all at once. So instead of having the leaving group pop off first, that rate determining step, the unimolecular rate determining step we just saw in E1, at an E2, you get a bimolecular rate determining step. So this is going to deprotonate that hydrogen 1 carbon away. This sigma bond is going to swing down and become a pi bond, and the iodide is going to leave all at once. Kind of cool, huh? Got 3 curved arrows in this one. And this is the only step of the mechanism. And since it's the only step of the mechanism, it's the rate determining step. And I wind up with an alkene again. Oh, I didn't do that. Colors, right? Oh, come on, Mark. Come on. Here we go. I need a green pi bond here. I like to keep my hinge on there, see where that came from. And then my iodide came off. And oh my goodness, come on. This is we'll talk more about it. This is T-butanol, tertiary butanol. We'll use that a lot for these things. Okay. Oh, wait, I didn't do something right there. I didn't do my color right. Oh, man. Yeah, I made the lone electrons. There we go. Okay. It's hard for me to talk and think about the colors and do it all at once. It's okay. All right. So there we go. Easy, huh? Does it seem familiar now that you've seen the E1 and now the E2? And then remember, we're doing the mechanism separate from the overall. So I'm going to draw out my overall products here too. Oh, and then I'm numbering carbons too. So let me see. I got this guy. I got the iodide. T-butanol. There we go. Let me count these up again too. So I got like 1, 2, 3 carbons, and then a fourth one there. Looking good. Over here, 1, 2, 3, 4. 1, 2, 3, 4. Got it. Okay. Done. We'll talk more about this, the specifics of this reaction, like that it's the hydrogen that's deprotonated 1 carbon away. It's called anti-periplanar. Its orientation needs to be in. But for our exam Wednesday, you don't need to talk about anti-periplanar. You just need to draw what I drew here. So if you drew this out, 5 or 6 times, I bet you have it memorized. And if you can like then visualize it in your head, you're good to go. All right, one more. WikiLeaks. Organum WikiLeaks. Okay, so for this next one, it's an SN1 reaction. So how many molecules are involved in the rate determining step if it's SN1? Yep, just one. It's a unimolecular rate determining step. So here we go. So what's the first step going to be? What's my first curved arrow going to be? Bromine leaves. Yep, that's the rate determining step. I'll make again a tertiary carbocation and a bromide. Is bromide a strong base? So what I'm asking also is hydrobromic acid a strong acid? Hydrobromic acid's an extremely strong acid. It's stronger than hydrochloric acid. So that means that bromide is a very weak base, even weaker than chloride. So it's even a better leaving group than chloride. All right, and then we have cyanide here. It's going to come in and add. And this is a substitution, not an elimination. So it's like the equivalent of SN2, but SN2, everything happens at once. Here it's 2 steps. So our cyanide, a great nucleophile, can add in now to the carbocation because it's not so crowded anymore. There was too much steric hindrance initially for this tertiary electrophile. This is a tertiary electrophile. Too much steric hindrance for SN2, right? But SN1 can happen because now after the leaving group leaves, that carbocation's trigonal planar is a lot less steric hindrance than when it's tetrahedral with everything in the way. And this one then produces let's tilt that a little bit. I'm gonna be good. I'm gonna draw this. No, it's not letting me do it. I'm trying to be good with the geometry here. It should be linear. So straight line to my carbon, and then the nitrogen should be 180 degrees to the bond there. So linear here, draw this right on the exam. Okay, there we go. So an SN1 reaction involves a unimolecular rate determining step, and then the cyanide adds on second. It's like SN2, but in 2 steps. So there you go. There you have it. That's 30 points for the exam. Just got to practice, get it down good. Now, I have some more help about this. Let me go to... So I've got the SN2 mechanism quiz coming up today. And then I have another mechanism quiz, but I'm not actually going to give you the quiz for this week. The reason why I'm not giving you the quiz for it is because you're basically getting the same type of assessment on the exam, the questions I just gave you. But I'm going to quickly click through these and you can click through them as well. Let me present it. So the first one I'll go through quickly because this is the same one you're getting on the quiz today, and I'm hoping you've already been practicing it, right? So this is today's quiz. In today's quiz, you're actually writing in all these details. And then you got the curved arrow mechanism. So it's SN2, so it's substitution, and it's nucleophilic substitution, and it's bimolecular rate determining step. So that's the rate determining step. It all happens at once, and the stereocenter is inverted. All right, we got it, right? And then, oh yeah, number your carbons. There we go. We got them all 4. And now SN1, this is a new one. We just went over once. Now let's try it again. I wonder if this is the same example. No, this one's a little different. Oh yeah. So this one, so this SN1 I'm about to do, it's a little more detailed than the one that you're getting on the exam Wednesday, but it's good. We're getting, if we talk about it now, it'll even make you more prepared for the easier one on the exam. So SN1 is a substitution reaction, of course, and then the N is nucleophilic, and the 1 is the unimolecular rate determining step. So here we go. What kind of electrophile do we have here? Is this a methyl electrophile? Primary, secondary, tertiary? Yes, secondary, huh? There we go. Good job. And so it's a secondary electrophile. Oh, what's the StereoChem on this one? Is this R or S? S. Bromine's the highest priority, then the ethyl, the methyl, and the H is back. It's an easy one, counterclockwise. So remember, it's so easy to mix up the R and S's. I want all of you on the exam to, when you're determining an RS, you'll write that down. You'll do some other problems on the exam and then come back with fresh eyes to look at it again. So always double check your R and S work. All right, and then we have sodium iodide and acetone is our solvent. This is an example of no, Ryan, you said, I want you to be able to do it in your head. Keep practicing in your head. Do a paper and head, Ryan. I want you to get to the point where you can do this quickly. All right, and now this one, the sodium iodide reaction and acetone, this is the Finkelstein reaction. Have I mentioned that to the whole class yet? I think I've mentioned it to some of you, Finkelstein. The Finkelstein reaction is something that this guy Finkelstein came up with, and it's just, basically it's all about the solubility of salts in certain solvents. Finkelstein. So the sodium iodide, it's fairly soluble in acetone as a solvent. But, so that's our nucleophile. And our solvent here, this acetone, it's something that we call polar aprotic. I'm going to go over that more shortly. You know what? I'm going to finish this one. I should be doing the rest of chapter 6 right now, but it's okay. Doesn't really matter. So polar aprotic. I'll talk to you more about that shortly, what that means. And then our products for this one, we get a racemic mixture. We don't get the inversion like we see for SN2. We get a wiggle here. And remember, the wiggle means that's a 50-50 mixture of wedged and dashed. Yeah. And now the reason why acetone's interesting for this Finkelstein reaction is when you use acetone, sodium iodide is soluble, but sodium bromide's not. And then sodium bromide will precipitate out of solution. This way, the reaction cannot go backwards when it precipitates out. And if it precipitates out, it can't go backwards. By Le Chatelier's principle, you get more product, more product. So I think of it as like Finkelstein's German chemist, and he's got his buddy, Le Chatelier, the Frenchman. And the Germans and the French, they fought wars back and forth throughout the years. But sometimes they get together and, like, you know, Le Chatelier's got a glass of wine. Oh, I like your reaction. It follows my principle. And then Finkelstein, Prost, he's got his big mug of German beer, hanging out, doing chemistry. So yeah, and this guy, racemic mixture, and that's our leaving group. Okay, so mechanism. What's the first step of the mechanism if it's a unimolecular rate determining step? Bromine leaves all on its own. Carbocations formed. This is a secondary carbocation. And then it's a rate determining step. And this is secondary carbocation. Oh, number of carbons. It's easy to mix these up. I just got a text to tell me the number of my carbons. 1, 2, 3, 4. 1, 2, 3, 4. Good. And then the iodide, which is not precipitated out, the sodium bromide will precipitate out. So because the bromide could go back and just add back on to the carbocation, but since it's precipitated out, now the iodide's the nucleophile that's left not precipitated, so it can add. And when the iodide adds, it can add from our side of the screen or from the back side. Because this is a trigonal planar carbocation, it's equally hindered on both sides. So if it comes from our side of the screen, is it going to be wedged or dashed? Yeah, from our side it'll be wedged. If it comes from the back, it'll be dashed. And so this wiggly line represents now, this is two molecules. The two enantiomers, the wedged and dashed, equal amounts. And we got it. Number of the carbons. 1, 2, 3, 4. Got it. All right, before I do the E1, let me pause there. I'll write down what I did. I wonder if this will paste. All right, and then SN2 finish. All right, here we go. So chapter 6, the one thing we haven't talked about is the solvents. So SN2 reactions are faster in polar aprotic solvents. Okay, so polar aprotic solvents, what's that about? So let me draw out some solvents, and then we're gonna figure out what these are. So I'll do N-hexane first here. And then I'll go ethanol. And acetone. DMSO. Okay, what's up with these solvents? So polar, non-polar, that should be easy for us. We've been doing a lot of that in lab. What's this N-hexane? Is this a polar or non-polar solvent? Non-polar. Non-polar, good. What about ethanol, polar or non-polar? Pretty polar. It's miscible in water. Water is like our poster child for polarity, right? Polar solvents. So that's polar. And then acetone. What's your guess? Polar or non-polar for acetone? Acetone's polar too. I think it is miscible in water too. Acetone. This CIBLE. Yep, acetone's miscible in water. I was pretty sure of that. Okay, let's go. All right, so acetone's miscible in water. DMSO, does that look polar or non-polar? I'm pretty sure it's miscible in water too. Is DMSO miscible in water? Yep, DMSO is interesting. It's soluble in a lot of stuff. So DMSO is miscible in water, and it's a great solvent for dissolving things, but it's a little bit slower than other solvents. Like sometimes you'll put something in DMSO to dissolve it, and you'll think, oh, it doesn't look very soluble. But then you walk away and come back in 10 minutes, you're like, oh, wait, it all dissolved. This kind of just, maybe it's a little more, because I think it's a little more viscous than water or something. But DMSO is an important solvent for that reason, because it's miscible in organic solvents. Water dissolves a lot of things. So it's used a lot, especially in like drug discovery. I remember when I was in grad school, I was trying to make drugs to treat cystic fibrosis, and I'd send all my drugs to get tested at UC San Francisco by first dissolving them in DMSO. Or I'd try to dissolve them in water, and if they didn't, then I would start adding DMSO to get it to dissolve. And so DMSO, it's interesting, and it's a great tool, but it could be dangerous. So by itself, DMSO is not too dangerous, but but the thing that makes it dangerous is that it can go through your skin easily. So if you get a little DMSO on your skin, it can like go into your blood, go through your skin and into your blood. And the DMSO, you don't want to be getting too much of that DMSO in your blood, but the DMSO alone is not too hazardous. It's actually used on horses. You can rub DMSO on horses like hips and things, and it like the kind of lubricates them, I guess, because it goes through their skin and it gets in there and helps them out. I don't think it's like prescribed by doctors for humans, but I have heard my friend who's like my old neighbor, he's a golfer at Sierra View golf course over by the mall, by the Arden Fair, no, by the what's our mall? Galleria Mall. And he said some of the old guys would put DMSO on their hands because it would help with arthritis for them. I don't know if it's recommended by doctors, but so DMSO can go through your skin. Now, the problem with that is if you have something poisonous dissolved in the DMSO, it can bring that poison into your skin too. So that's where you got to be careful. So if you're working with something that's poisonous and you're dissolving it in DMSO, you want to wear gloves so you don't get that to go through. You don't want it to be bringing no poisons into you. And there's a book and a movie. It was like an Oprah book. I don't know if anybody's heard of it. The White Oleander. Yeah, so I guess the White Oleander story, spoiler alert, the wife kills her husband, I think, by taking white oleander plants and putting them in DMSO to extract their poison and then rubbing it on him. And you've seen the oleander plants everywhere. They're really common. They tend to be like on the side of freeways a lot. They're out in front of like businesses and stuff. I think you need to see the whole thing. I don't know. That's probably not it. So yeah, you got to be careful with DMSO because of that. Okay. And also I heard there was a chemist who killed his wife by taking a cigarette and putting the cigarette tobacco in DMSO and then letting it extract out the nicotine in the DMSO to a high concentration. And then he rubbed the DMSO nicotine on her, so it would give her a nicotine overdose. And I think the police were like, what the heck? Why does she have DMSO on her body? Oh, she nicotine overdose? Oh, he's a chemist? And they figured it out. So yeah, crazy. Okay, so little sidetrack there. Yeah. All right, so now we got polar, nonpolar. Now there's something else. There's something called protic and aprotic. So if you're protic solvent, that means you can hydrogen bond. You're protic. And then as we've seen before, when you put A in front of a word, it like makes it the opposite, right? Atypical symptoms or like achiral. So aprotic, you cannot hydrogen bond. So speaking of that, is hexane protic or aprotic? Hexane is aprotic. It cannot hydrogen bond. So hexane's nonpolar aprotic. What about ethanol? Is that aprotic or protic? Protic. It can hydrogen bond. It has the hydrogen there. And remember, Hydrogen bonding is defined as the following. Hydrogen bonding, it has to be some atom X attached to a hydrogen and then another atom X that's attracted to it, because the 1X over here has a delta minus, this one has a delta minus too, and then the hydrogen has a delta plus. Okay. Oh, and then I should be more specific. I'm sorry. So protic means you can hydrogen bond, but it should be more specific. It should be you can hydrogen bond, and you are the hydrogen bond donor. Okay. Hydrogen bond donor. What do I mean by that? This is the hydrogen bond donor, the one that's got the hydrogen, hydrogen bond donor. This one is the hydrogen bond acceptor. ER acceptor? Oh my goodness, I'm so bad. X, is there two C's? I don't even know. ACCEPT. Yeah, lost it already. ACCEPTOR. OR, not ER. Okay, so does ethanol, can it be a hydrogen bond donor? It sure can. It's got a hydrogen on an oxygen. Oh, I didn't even define that yet. Sorry. I'm all over the place with my definition here. And then also X has to equal either fluorine. Well, I'll type it up the other way. Has to be nitrogen, oxygen, or fluorine. It's got to be one of those three. That's by definition. Other atoms are very electronegative, but it's those ones. And so I do have on this ethanol, oxygen to a hydrogen. Yep. So I know I'll have a lot of delta positive on the hydrogen. It can hydrogen bond. Delta negative on the oxygen. All right. So now what about acetone? Is acetone protic or aprotic? Acetone is aprotic. Acetone does have hydrogens. It's got 6 hydrogens, but these hydrogens are on carbons, which aren't very polarized bonds, right? I would actually say the hydrogen is slightly more electronegative than the carbon because it's an sp3 carbon, but they're pretty much the same. Whereas when the hydrogen's attached to nitrogen, oxygen, fluorine, then it's like very polarized. And then you get hydrogen, you get down. What about the DMSO? Is that protic or aprotic? Aprotic again, pretty much the same as acetone, huh? Got a carbon here, sulfur there. Yep, so they're both polar aprotic, and SN2 reactions are much faster in polar aprotic reactions. Let's look at some data for that. If I go to chapter 7. Oh, Aliana, I don't know if you're here. Is Aliana here? You were asking me about this. No, I don't think she's here yet. Okay, so she was asking about the downloadable version of chapter 7, and I'm not sure how it works, but I got the online version here. So here we go. We got a bunch of solvents to choose from. And to describe, let's talk about these ones. So what do you say? Are these polar solvents? Come on, iPad. So the acetone we already talked about. This acetone is polar aprotic. What about this HMPA? It looks pretty polar to me. And it is. It's got polarity there, right? And is it aprotic? Are these hydrogens on an oxygen, nitrogen, fluorine? No. So this one is also polar aprotic. Okay. And the same goes for all of these. So that's, and the reason why we list them is these are common solvents that are good to use for SN2 reactions. And I've been throwing them out there, right? We did some DMF, some HMPA, DMSO. I haven't shown you nitromethane yet, but there's nitromethane. Okay, and now we're good at identifying these solvents. Let's look at some data for them. So let's start off with methanol. What kind of solvent is methanol? Is it polar? Methanol is polar. Is it protic or aprotic? Protic. Yep, so its SN2 rate is slow. We're going to sign it as 1, so the other ones are greater than 1. Okay, and then formamide. Formamide looks like this. Formamide. It's like an aldehyde, amine kind of combo thing. So formamide, is it polar, do you think? Yep, it's polar. Is it protic or aprotic? Protic. It can definitely hydrogen bond. It's got the NH. Okay, then we got N-methyl formamide. It's got 1 methyl and 1 hydrogen on the nitrogen. N-methyl, and the methyls on the nitrogen. That's where we go. That's how we nomenclature it. N-methyl. Okay, so is this one polar, protic, polar, aprotic? What do we got here? Still protic because we have 1 NH, but the reaction rate went up a little bit, went from 12.5 to 43. But here's where the big jump happens. This is DMF, NN dimethyl formamide. So this one, DMF, is polar, protic or aprotic? Aprotic. It's got no hydrogens on the nitrogen now. We've replaced all the NHs with methyls. And look at that jump. 1.2 million times faster than methanol. So when you go to polar aprotic solvents, the SN2 reaction really jumps in rate. So that's why I've been doing SN2 reactions all along. You've probably noticed I'm using acetone a lot. I'm using DMF, DMSO, because when you use polar aprotic solvents, it really favors and speeds up SN2 reactions. All right, so why is that? This is how I think of it. When I have, say, like hydrogen sulfide as my nucleophile, and then I got a good like SN2 electrophile here, right? So my SN2 electrophile wants to come in and kick off that bromine. To do the SN2 reaction, right? There we go. All right, so as this is occurring, the polar, if you have a polar protic solvent, say like ethanol, or actually I'll make a methanol since that was in our table, right? So if you have methanol, it can solvate the nucleophile strongly. So there's a strong interaction between the solvent and the nucleophile. So I think of them as maybe like paparazzi. They're surrounding the nucleophile and making it hard for it to do its backside attack. Because if I have like, say, 4 or 5 methanols all surrounding this nucleophile, then they're in the way of it getting to the electrophile. So you could think of it as like I don't know how to spell paparazzi. One Jamboard, come through for me. Come. Oh, oh, oh. Here we go. Here we go. It's gonna work. Yes, like paparazzi. All right, so that's how I think of it. Okay, so that's what a polar protic solvent does. But since the transition state will have partial charges, it still needs a polar solvent. But polar protic's just kind of too polar. So the transition state has partial charges. It still needs a polar solvent, but polar protic is just too polar. All right, that was good. So let me show you what I mean. The transition state for this one is going to be, this is going to be exothermic. So I'm going to go, boom, boom, boom. This bond is almost completely formed. And that's there. And then the bromide is far away. Okay. This is our transition state. And so what's the charge on this sulfur? It starts off -1. It's almost a full product. What do you think the fractional charge is on sulfur? -1/4. It's almost to 0. It's 0 on the product side, right? So it's almost there. -1/4. What about the bromine? What's its charge? Bromine is going to be -3/4 because it's almost fully negative. Okay, so there's charge in the transition state. So you want a polar solvent to be able to help out with that charge because that'll lower the energy of the transition state and make it go faster. But if the solvent is too attracted to the nucleophile, it can't quite get all the way in and do the thing. So it turns out that the polar aprotic seems to be just the right amount of polar. The polar aprotic is polar enough to help stabilize transition state, but not too polar to solvate. I know I said too much and too much. I hope it's making sense. Okay, so yeah, or at least that's our, what we say, hand waving. That's how we think of it. And because we run the experiments, you get your experimental data. You know, you get this data, and then you just try to make up stuff to make it make sense. And then whatever you make up, you do other experiments, and if it supports your BS, then you just keep saying it. At first, you say it was a postulate, then maybe a theory, and then it becomes a law. I don't know, whatever you want to call it. Okay. So, yep. Oh, I think of the paparazzi. I like the paparazzi. So when you have polar protic solvents, they just solvate the nucleophile, surround it too much. It's trying, this poor sulfide is trying to get in to get a cup of coffee. He's got his cameras in his face and her face, and they, forget it, they leave, or their face. And then if it's a polar aprotic solvent, the polar aprotic solvent's more chill. It's like the star has their sunglasses on and their beanie and their hoodie. They're just cruising in. They can get into that coffee shop, get a coffee, and leave without too much trouble. All right. We're done with chapter 6. I think that was the last thing of chapter 6, huh? Yeah, I guess I didn't mention it. Just a fun fact, nucleophiles are toxic. You gotta be careful with them because they can attack things in our bodies. So like I said, what was it? Azide, the N3 minus azide, that's a poison. So a lot of them are poisons. Gotta be careful. Cyanide, that can kill you, right? Cyanide tablets. Okay, so we finished chapter 6. We already actually kind of started chapter 7, huh? So I gave you those mechanisms. Why don't we take a break and then we'll do some more of chapter 7. What does the E in E1 reaction stands for? So the E is for elimination. So in an E1 reaction and an E2 reaction, you're eliminating parts of the electrophile. The electrophile gets eliminated from it, a proton from its hydrogen and the leaving group. Whereas the S in the substitution reactions, the S stands for you're substituting a leaving group for a nucleophile. So substitutions, you're losing something and gaining something. You're substituting things, but the elimination reactions, you're actually just like overall losing a couple things from the molecule. Okay, so before I go into the outlines of chapter 6, I'm going to show you I like these grumpy carbocations. This was made by a student of mine back in 2006, so what, 5 years ago. This is Max's, we came up with this, I don't know why we came up with the grumpy carbocation, because it's cat, it makes sense. So this is the grumpy carbocation. So we already know about, oh wait, is there any other questions besides that one, Max? Not Max, Raphael's question. Did I say 2006? I meant 2016. So grumpy carbocation does not have the positive vibe. He's positively grumpy. So here's what I was thinking. It's interesting that's already there. How did I move this? Animate transitions. Oh yeah, it makes sense that it's there. I'm just not presenting yet. So here's the grumpy carbocation. So carbocations are much like radicals. Carbon radicals, they can get help from other sp3 carbons attached to them, because we think of the sp3 carbons as electron donating. So remember how a tertiary carbon radical is lower in energy than a secondary carbon radical, then a primary, then a methyl carbon radical. Well, the carbocation, same trend. The tertiary carbocation, which is represented by this letter C and the plus sign on the carbon's face. And then these mice are like methyls. So this is the tertiary carbocation. You can think of it as like this guy, right? So this tertiary carbocation, it doesn't have an octet. It actually only has 6. Its octet count is 6, so it's 2 short of an octet. Where a radical, it's only 1 electron short. So, but carbocations are even higher in energy. But the tertiary carbocation would be the lowest in energy of the carbocations. And so the grumpy carbocation says, "Reach for the stars," said the tertiary grumpy carbocation. "Just wear deodorant." And then so the reason why we are talking about this is because the SN1 reaction, it involves a carbocation intermediate, and the E1 also involves a carbocation. All right, and then the secondary carbocation looks like this. It's got a carbon in the middle, missing electrons, and it's 2 short of an octet. And so it has a positive charge. And then 2 neighboring methyls are helping out, but it's only 2 neighbors helping out. The hydrogen that's attached isn't helping. And so it's higher in energy than the tertiary. And now, so these two, the tertiary and the secondary carbocation, we're going to see these all the time. They're common. But the methyl carbocation, it's so high in energy that we won't even really see it. We won't, unless it has resonance, but then it's not really just a second primary carbocation. But the primary carbocation, it's too high in energy for practical senses. So that's a primary carbocation there, right? It only has 1 carbon to help donate to it. And then the primary carbocation says, "You'll reach me," says grumpy carbocation, "when your mom flies." I don't know if that's too much. And actually, Max was a really nice student. I actually made up these bad jokes about the grumpy carbocation. Okay, next up, the methyl carbocation. So the methyl carbocation is the highest in energy. That's up in the catosphere. So high, too high in energy for us to really make. So we're not gonna, if you're on an exam or on a homework, if you draw out a primary carbocation or methyl carbocation, something's wrong. That's usually always so. Don't do that. So you think you'll reach me, says methyl grumpy carbocation. That lipstick on your forehead will not help you make up your mind. So there's some cheesy jokes here. All right, so drawn by Max. Wait, your screen sharing is paused. Did I just, can you see my screen? I don't know why it's saying your screen sharing is paused. It's scaring me. I'm gonna stop and restart it. I don't know what's up with that. I'm still recording, good. Okay, I don't know what was going on there. Okay, so yep, we got that one. So now let's go back. So we already looked at the SN1 mechanism, a real simple one. Now I'm gonna do one that's more complicated, and we'll talk more about it. Yeah, so here it is, pick an overall reaction for this. Oh wait, is this what I want to do? I don't know where I'm at. There we go. So we're going to keep the overall reactions and the mechanisms separate. So here first, overall. I'm going to go with an electrophile that's going to give me more than one product. Let's do this one. Bromine. And I'll use water, yeah. And if you want SN2 to be favored, because we're going to see shortly, these reactions we've learned, the SN2, SN1, E1, E2, they're all in competition. So sometimes you can get more than one of their reactions to take place. Sometimes you only get one. But two that are in competition pretty much always, almost always, is the SN1 and the E1. But if you cool an SN1 reaction, it helps favor the SN1. If you heat it, it favors more of the E1. We'll go into that more. All right, so there's the overall reaction, and then we're going to have the mechanism down here too. Let me start with the mechanism. So if it's an SN1, that means it's a substitution and it's got what kind of rate determining step? Unimolecular rate determining step. And it just involves the leaving group leaving. There's going to be a hydrogen here. It had the one hydrogen to begin with, right? That was like wedged out. And now it's in plane, it's trigonal planar. And also, is this trigonal? Oh, let's actually, before I do that, let me name these things. So what do I call? Give me some names for this. How can I describe this bromide here? Electrophile, good. Even more specifically, a secondary electrophile. Good. We got our secondary electrophile. It forms the carbocation, and this carbocation is what kind of carbocation? How would we describe this carbocation here? Trigonal planar and a secondary carbocation. And we saw just before this that the secondary carbocations, they're higher in energy than tertiary, but they're a reachable energy. They can be made, and it's trigonal planar. Also, this secondary electrophile initially, is it chiral or achiral? Chiral. So we start off with a chiral reactant. When we have a chiral reactant, we don't necessarily get chiral products, but we might. And yeah, is this guy R or S? It is S, huh? It's got the S stereochemistry right there. And so this is a chiral reactant, but then right when we come to this carbocation, is that chiral anymore? No, this is achiral. So in the first step, we lost chirality. So this reaction is going to be, it's starting with a chiral reactant, but it's not going to end with chiral products. Okay. Forgot my bromide too. Beep, beep, there it is. BR. So this, our unimolecular rate determining step, that's the one of SN1. And then what happens next? The water here. The water is a, would you think of it as a strong nucleophile or a weak nucleophile? Water is a weak nucleophile. It's got no charge. Its oxygen's pretty electronegative. But that's okay in this reaction. We're still going to get a good yield because the carbocation is a very strong electrophile. So the water can come and add on to, from our side to be wedged or from the back side to be dashed. It adds on both sides. So it's like this. Oh, oops. Oops. I know adding color helps you all, but man, sometimes this slows me down a lot, but it's good. It's good. It's all good. So I'm going to get wedged and dashed. because that trigonal planar carbocation has same steric hindrance on either side. And then we can abbreviate that. Actually, let me just finish off this part too. Oh, what am I doing? Never mind. We can abbreviate these two. So these two together are just, we draw the wiggle. And that's primarily how I'll be doing it. So this is a wiggle, not a dashed. Huh? There's definitely a difference there. Okay, so there's that step. And then the final step of the mechanism is another water molecule will come along and deprotonate this. And that'll happen for both of them, you know. Little guy here. And the product of the final product can be drawn up this way. There we go. So our overall reaction, let's go back to that. I kind of didn't give myself a whole lot of room for this, but we'll make it work. I got it. Overall reaction, wiggle, wiggle, wiggle. Racemic mixture of the secondary alcohol, hydronium, and bromide. Oh, wait. Yeah, this is SN1. That's right. Okay, yeah, this is good. I do want you to write out the overall reaction separate from the mechanism, and I don't want curved arrows in the overall. It messes you up. Okay, so in this reaction, the water is playing two roles, this water molecule. Well, it's kind of playing three roles. I should say this guy, this water. I'll type it. What are the roles it's playing? What would you describe it as? Can anyone help me out with this? So one, it's being the what? It's the nucleophile. Yep. Cool. What else? The solvent. Yeah. It's the solvent. And third, it's the base. It's deprotonating the water after it added. So the term for this, when a solvent is also a reactant, we call it something, it's called solvolysis. So that's just a term I started off the chapter with here, right? Solvolysis. And solvolysis, sol sounds like solvent, right? You can tell. And lyse means to cut. Have any of you come across in like biology classes lysozymes? Have you heard of lysozymes? So lysozymes are proteins that cut up other things. Lysozymes. So lyse is to cut. So solvolysis, solvents cutting up the molecule, reacting it. Okay, and now the rate law for this is the following. Rate laws are always just some rate constant with my cursive K right here. Let me see if it looks like a K. Does it look kind of like a K there? Times the concentration of whatever's in the rate determining step. So what's in the rate determining step for this reaction? What reactant is in the rate determining step? The electrophile. So it's only dependent on the concentration of the electrophile. If I like double the concentration of the nucleophile, the water, well, in this case, the water is the solvent too, so it's kind of funky. But if I, yeah, I have to show you a different example to get that point across. But yeah, so there's the rate law. Let's look at some examples of what I'm talking about. I'll do it on the next slide. SN1 versus SN2. So SN1, it's equal to K concentration of the electrophile. It's said to be first order. Whereas in an SN2 reaction, rate constant K. And now what molecules are reacting in the rate determining step of an SN2? The electrophile and the nucleophile. Remember in SN2, the nucleophile does the backside attack, kicks the electron out all at the same time. So an SN2 reaction is a second order reaction. So like a common question you might find on a chemistry GRE exam or an ACS exam or an MCAT or maybe a DAT for dental school or something would be something like this. If you double the concentration of the nucleophile and the electrophile, how will it affect each below? So for an SN1 reaction, doubling the concentration of the nucleophile, what did I say, nucleophile? And the electrophile, yeah. If I double both of those, the rate just doubles. Because now I'll have my rate law will be K 2 times the concentration of the electrophile. The nucleophile is not in the rate law. But for how does that affect the rate of SN2? Quadruples. Because now we've got to consider both the rate of, it's going to be double the concentration of the electrophile and double the concentration initially, the initial concentration of the nucleophile. So that's 4 times as fast, right? Another one I like. What about, and also this type of question is related to the experiments that help us, determine the mechanism. So when professors are coming up with mechanisms like this, they think, oh, it looks like maybe the carbocation forms first and then something adds because of the stereochemistry. Then they're like, oh, if that's the case, then when that carbocation is formed in the first step of, say, an SN1, that should be the rate determining step. This should be a first order reaction. So then they test it. They run the reaction with a certain concentration electrophile, and then they change it, and they graph it and figure out, oh yeah, looks like it's first order or second order, and that supports the mechanism. So another one like that is, what if you keep the moles of electrophile and nucleophile constant, but double the solvent? So for an SN1 reaction, what will happen? For the SN1, it will cause the concentration of both things to go in half. So if I double the solvent, their concentration gets cut in half. Actually, I'll write it up here first. So the SN1 reaction is going to be slower. It will be half the rate. It'll be, concentration of electrophiles half. And then what about SN2? SN2, it will be 1/4 the rate. Will this question be on the exam? Annalise is asking. That could be on exam. This could be on exam 4. Do we have an exam 4? We just have a final exam coming up, huh? It won't be on exam 3. Exam 3 for SN1 will only have the question I gave you related to SN. Well, it could be that question, and it also could be the reaction coordinate diagram, but it won't be these specific details. But on the final exam, it can, yeah. That's my train of thought there. It will be 1/4 of the rate. Yep. So here, I'll write it out here. So it's going to be K 1/2 the concentration of the electrophile, 1/2 the concentration of the nucleophile, so 1/4. Whereas the SN1, it's just K 1/2 electrophiles. That's all it is. And then the other thing, like on an MCAT or something, you'd see they'd say, oh, we're running a reaction. We weren't sure if it was SN1 or SN2, so we doubled the concentration of the, we doubled the solvent, and this happened. And then if it went half as fast, then you say it's SN1. If it went 1/4 as fast, you say it's SN2, that kind of thing. All right. And yep, so now getting good at this. Oh, potential energy diagram. Let's do it real quick, and then we'll call it quits on that point. So those details won't be on exam 3, but the reaction potential diagram could be on exam 3. Because I've been asking you these energy versus reaction coordinate diagrams forever. With like if I just tell you if the first step's endo exo, you can figure it all out, right? You didn't even need to know it was SN1, SN2, or anything. Okay, so here we go. We start off with our electrophile. What was our electrophile? Bromide dashed. And the first step, the bromide just leaves. Is that going to be endothermic or exothermic when this bromide just leaves on its own to make the carbocation? So we're only breaking a bond, endo or exo. It's got to be endo because we're breaking a bond. It takes energy to break bonds. And then the water molecule comes along, and that step's exo. I don't know if it's lower in energy than the reactant. So but I will tell you it's exo. So just make it exo and you're good. And the reaction's overall exo. So we get initially a protonated alcohol. And then another water molecule comes by, deprotonates it. Bloop, bloop. There we go. Let's add in our arrows, activation energy arrows. Make sure we start them at the right spots. So what's special about that first activation energy arrow? It's the rate determining step. And is it the longest of them? Yeah, looks like the most activation energy. That'll be the slow step. Okay, and now the transition state for that one. It's going to look more like products. So I'll draw it this way. That bromide is going to be almost completely off. And what kind of charge will it have? It's going to look almost like the product. So the carbon is going to be about +3/4. The bromide is going to be almost all negative because it's almost done and it ends up -1. So it's -3/4, right? Okay, transition state 2. We've got the water coming onto there and it's going to look more like reactants. It's closer to reactants, so the water is going to be far away. And so the carbon is still going to have a lot of positive charge. And the water is going to be just starting to get its positive charge because it hasn't really reacted much. Okay, final step, transition state 3. The oxygens here, we got it. It's looking like reactants. So this bond should be shorter and this bond should be longer. And our charges are for the oxygen on the carbon. It's still pretty positive. It's just starting to lose its positive. So I'll put +3/4. And then the oxygen, the water that's gaining +1, +1/4. That all makes sense?